Hello and welcome to day 1 of 8.3 lesson. And we're going to talk about Oreos today. Who doesn't love Oreos? Well, right now what we have is Mr. Gutchock, not Mrs., but Mr. Gutchock. All right, wanted to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. So he selected a random sample of 30 cookies and found a weight of each cookie. The mean weight was given right there. All right, with a standard deviation that he found of his sample right there. And we want to make a 95% confidence interval to estimate the true mean weight of the Oreos. All right, so like we did it with proportions, now we're talking about means. And so just like proportions, we need to find a point estimate. Now our point estimate is the true mean that we're trying to find. And we're going to use our statistic, which in this case is our mean, which is 11.1921. All right, that is our point estimate. All right, essentially the sample mean that we found from our sample. And so now we're going to identify all the different things that we have here. So right here we're going to identify our population. Now the population we're going to do is all Oreos. The parameter we're using is mean, okay, and that we're looking for is the true mean weight of the Oreos. Okay, true mean weight of the Oreos. We took a sample of 30 Oreos, and we got a statistic, which is actually our point estimate, as we found up there. So we got a statistic of 11.1921, and that's our mean statistic, along with our standard deviation that we also have up there as well. Now from here, we're going to go through and check some of the things that we want to do. All right, we're going to check our conditions, just like we did with the proportions. We're going to do the same thing. So we're going to take a random sample of 30 Oreos. Okay, 30 Oreos, and this is going to go. And the reason why it has to be random is I failed to mention this in proportions, but I'm going to mention it now. Is that yes, we want to try to reduce bias in our sampling procedure so we can get close to the true parameter. But also one of the key things is we want to be able to generalize. And that's the reason why we take a sample of a population. When you take a random sample of a population, it allows you to generalize to that population. And since we're looking for the true mean weight of the Oreos, it's going to be important that we do take a random sample of the actual population of Oreos as well. Okay, so it's for generalization purposes. The next thing we're going to do is we're going to find the formula for calculating the standard deviation of this. Now, to calculate the standard deviation, if you recall from the last chapter, what we were doing is that we take our standard deviation, all right, from our sample. All right, so when we have this, actually our standard deviation is normally we take that from our means, okay, is we take that divided by the square root of n, okay, square root of n. Now, in this case, all right, we don't have the true standard deviation, and this kind of goes down to question number 6. So we're actually going to use the sample standard deviation, all right, and then we're still going to divide that by the square root of n. Okay, so now can we use this condition? Well, if you recall, you can only use standard deviation of a sample without replacement. All right, is if it passes the 10% condition. And yes, it does pass the 10% condition. 30 is definitely less than 10% of all Oreos. And so we are pretty set there. Okay, now from here, in the form of the standard deviation of the sampling distribution, all right, of that we don't know the value of this. So we're going to find the standard error. Okay, so we're going to use this. And so we're going to say this is actually our standard error. Okay, because we don't know what the true standard deviation is. And so, all right, to figure this one out, our standard error is we're going to take our sample standard deviation divided by the square root of n. So in this case, what is our standard deviation? It's going to be 0.0817. 0.0817. And we're going to divide that by the square root of, I believe it is 30. All right, we have 30 Oreos. And so if you put this in your calculator, and you take that 0.0817, all right, and you divide that by the square root of 30, you'll have a standard error of 0.0149. All right, somewhere around there. Okay, now from there, we're now going to our last condition, and this condition is this approximately normal? Okay, because normally we have to find our critical value when we find an interval. All right. And the answer is yes. Because we're using means, if you recall, when we use means, we can use this thing called the central limit theorem, and this is where we can use the n value. And yes, n, our 30, is greater than or equal to 30, so we have a large enough sample size. All right, so this is approximately normal, okay? So approximately normal, that is okay. All right, and so we'll have that right there. All right, now, from here, the question is, when finding the margin of error confidence, for a portion, we use a z critical value. For means, however, because we don't know this true standard deviation, we're going to use what's called a t as our critical value. Why? Now, what is this t value that we're referring to? Well, it comes from here, all right, my friends? Now, we have a t distribution, which is known as a student's t distribution. And reason why we use a t distribution, it's used for means, okay? It's used for means. And it's when we do not know this actual true population standard deviation, which is pretty much most of the time, okay? Because most of the time we don't know if we have this true standard deviation of the population because we didn't find the actual population itself, because normally we're taking it from samples. And so what we have with a z distribution, and if I kind of like highlight it right here, all right, and let me get my highlighter right there. And if you go right here, we notice that the normal distribution will look like this with a standard normal curve with all of our current standard deviations. But what a t distribution does is that when you have a t distribution, it changes, all right, the curvature based on the n value, the sample size. And so when you have a small sample size, what happens is that it actually flattens out and creates a larger, all right, values, okay, a little bit higher values, a little bit more area, all right, because we are not sure of that, because it creates a little larger variance, okay, a little larger standard deviation that we're going to be using. And so it takes that into account. In the same way, when you have a larger, okay, so right here, if you have a larger value, you see what happens is that this curve, all right, actually becomes more like a normal curve. And in essence, when this keeps on increasing, so if n keeps on going to infinity, all right, we actually get this value when we calculate it would actually look like a z curve. So we call this a t distribution, which is really based on the n value, okay? And so there are special tables that are used for a t distribution. Okay, and these are used for critical values that can be used when you find anything with means and where you have to use this. Okay, and so here we have is what t is needed for the confidence interval. All right, if we're doing a 95% confidence interval. Well, in a t distribution, you have two different things, okay, that you need. All right, you have the degrees of freedom that you're looking at. Okay, and also you need to figure out what is the, all right, area of the side you're doing. So instead of being a percentile, it's really something that is above that we're looking for. And so when we're talking about, all right, a t distribution at 95% confidence interval, okay, we would use a inverse, all right, t, all right, inverse t distribution, where our area would be, yes, 0.05 divided by 2, all right, which we know is going to be 0.025. All right, so we put that in there, 0.025. And then instead of having a mean and standard deviation, well, with a t distribution, we don't use the mean in that, we use the n value and actually what's known as degrees of freedom. All right, degree of freedom. And our degrees of freedom are how is this curve going to be? All right, we're going to be kind of setting the curve that we want. And in order to figure out degrees of freedom, it's always going to be n minus 1. And usually it's whatever the sample size is minus 1 because we're using a single variable. Okay, and so right here, our degrees of freedom, because we have 30, it would be 30 is our sample size minus 1, which would be 29. And so looking at this, we can see that we can go down to 29, right there. We can go at our tail, which is at 0.25, and we kind of follow this right there along this, and we see, okay, it's going to be right there. But also, if you look at the bottom, you see how it says confidence interval. All right, and you can see that's going to be, our t-value is 2.045. So this is definitely a little bit different than what we had before. Okay, 2.45. So over here, what we can find out is that we have a t-value of 2.045. And so now, how do we calculate a margin of error? Well, we calculate the margin of error the same way, very similar way, that we do with the proportions one. We got to find our critical value. In this case, it's our t value. So we're going to have 2.045. And then we're going to multiply that by our standard error. Okay, our standard error. Now, if we go a little bit back, all right, what was our standard error again? And we found our standard error to be 0.0149. All right. And so we'll go back over here. All right, and we'll multiply that by 0.0149. And so we'll find our margin of error. If you take out your calculators, you can calculate this out. And we'll have a margin of error of 0.0305. I'll just round it to 5. That's what I got. Hopefully it's something similar to what you have as well. So now, when we calculate the 95% confidence interval, well, we take our point estimate. And if you recall what our point estimate was, going back, all right, you probably have this already there. All right, but we have our 11.1921. All right, and we take that point estimate from our mean, which is 11.1921, and we're going to plus or minus our margin of error, which we can see our margin of error is our, all right, critical value times our standard error. And so I'm going to add this to 0.0305, 0 right there. And so we're going to add that. And what we have is our upper bound is going to be 0.2223. And then we'll have a lower bound. And if you can do that, you can figure this out too. It's 0.0305, and then I get 11.1616. All right, and so that is where our interval is. So what do we just find here? Okay, let's interpret this. So I'm going to type this out real quick. All right, what we said is we, get over here. Come on now. All right, make this a little bit smaller. And we'll make it a little longer. All right. We are 95% confident that the true mean, all right, weight of Oreos is between, is captured between 11.1616 and 11.223. And I have to go back here real quick. And is that in ounces or what is that? Grams, I'm sorry. All right. And we're going to come back over here. Let me finish up. Grams. There we have it. We're 9% confident the true mean weight of Oreos is captured between 11 and 11 grams. And that's what our interpretation of the interval is. So if we had to write a specific formula for a confidence interval for the mean population, all right, for a population mean, all right, well, we have a general formula, which I already said up here, all right, and so it would just be, all right, we take our point estimate, plus or minus our critical value right there, which is our t-interval, times our standard deviation, which is going to be our standard deviation of the sample over the square root of n. Okay, and that is our general one. And then according to Misko, the Oreo weight is 11.3 grams. Does our confidence interval provide convincing evidence that the true average weight is less than 11.3 grams? Well, if looking at this right here, 11.3 is not on that. And so I guess the answer is yes. 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 All right. Our interval does provide convincing evidence because, all right, 11.3 grams, all right, uh, is not on the interval. Maybe I should say because, all right, the interval contains values below or less than 1.3 grams. That probably makes more sense. All right. So yes, the interval does provide convincing evidence because the interval contains values less than 11.3 grams. Okay. All right. It should say all values, all right, less than 11.3 grams because it doesn't contain some. It contains all the values less than that, and that's why it is convincing evidence. All right. So I hope that makes sense. I hope this is a good video to get you started on better understanding how we can create confidence intervals for means now. Also get the introduction to how to use a t-value for a critical value. I have other videos going through some trick understanding and also notes on this. So pray this serves you well, and good luck and God bless in the rest of your problems.